Hello! For the Summer of Math Exposition number 3, I put together an interactive to guide you through a series of programming puzzles in order to learn the esoteric programming language FRACTRAN. FRACTRAN was developed by John Conway in order to reason about the Collatz Conjecture and Collatz Conjecture-like problems. In particular, the fact that FRACTRAN is Turing Complete tells us that there isn't some really powerful tool that we can use to solve all Collatz-like problems. I'll talk about that more in a separate video, but in this video I would like to walk you through the programming puzzles in the interactive that I made. I highly recommend that you give the interactive a try. Probably the best way of learning a programming language is to actually program in it. And I hope I've done a good job of designing these puzzles to slowly build up your programming knowledge in this language. I'll link to the interactive below, and I'll also link to a video that I've already made that kind of guides you through how to get started entering your programs into this interactive. But if you're stumped on one of the levels or just want a video lecture on why FRACTRAN is Turing Complete, this video is for you. So let's talk about programs in FRACTRAN. A program in FRACTRAN is a list of fractions, and it's designed to take in a natural number and output a natural number. And what it does is we take that natural number and we multiply it by the first fraction on the list that gives us a natural number as a result. Very often when we're programming in FRACTRAN, we'll have specific inputs that we want to get mapped to specific outputs, and then everything else, we don't really care what happens to it. So the first programming puzzle is to find a program that takes in as input 2 and outputs 3. Now if you input any other number, I don't care what the output is. I don't care if it even gives you an output at all. But it has to be the case that if we input a 2, we get a 3 as output. Well, remember that a FRACTRAN program takes in the input and multiplies it by a fraction in the list. So what fraction can we multiply 2 by in order to get 3? Well, 3/2. So this here is our proposed program, and let's check to make sure that it works. When we input a 2, we go through our list of fractions, and we multiply that 2 by the first fraction in our list that we can multiply by to get a natural number. That's 3/2, so we multiply 2 by 3/2 to get 3. Now we're not quite done. A program in FRACTRAN will keep applying this process. Keep taking the number that we have. We started off with the number 2. Right now we have the number 3. It will take the number that we have, the number that's stored in memory, and continue trying to multiply it by a fraction in our list. So we take 3, we try to multiply it by some fraction in our list that gives us a natural number. Well, there's a problem. This fraction, the only fraction in our list, all of the fractions in our list, if we try multiplying by 3, we don't get a natural number. And so the program halts and outputs the number that we're currently at, in this case 3. So this program does in fact take 2 as input and outputs 3. We just needed to check to make sure. By construction it takes 2 to 3, but we needed to make sure that it stopped at that point, that it didn't take the 3 and turn it into something else. If there was another fraction in the list, like, I don't know, 5/3, then it would take that 3 and multiply it by 5/3, and we don't want that, not now. So the solution to this problem is just the program 3/2. Programming puzzle number 1 asks us to find a program that when we input 2 outputs a 3, and when we input 5 outputs a 7, and if we input anything else, it can output whatever it wants. It can even go into an infinite loop. I'm not checking those things. Well, how did we turn 2 into 3? We multiplied it by 3/2. So let's try including that in our program. Now, at this point, this 3/2 will turn this 2 into this 3, and 5 will completely bypass this 3/2, right? If we input 5, we can't multiply 5 by 3/2 to get a natural number, so it will completely ignore this 3/2 and move on to the next fraction in the list. And we can simply have that next fraction turn 5 into 7. That is the fraction 7/5. Let's check to make sure this works. If we input a 2 into the program, gets multiplied by the first fraction in the list, that is 3/2, to get turned into a 3. And then we try running the program on 3. We try multiplying 3 by each of these fractions, and we don't wind up getting a natural number. So nothing happens, and we wind up stopping at 3. So if we input 2, we output 3. If we input 5, well, we try multiplying 5 by 3/2. That doesn't work. We multiply 5 by 7/5. That turns into 7. And then we try running 7 through the program. And again, that's not going to work. And the key thing to check here is that if we're trying to figure out if a certain number can be multiplied by one of these fractions, we just have to check the denominators of the fractions. We just have to check, assuming that the fractions are in lowest form, whether or not, for instance, 7 is divisible by 2 or divisible by 5, which it isn't. They're all prime numbers. Now, sometimes in order to get a better sense of what programs in FRACTRAN do, it helps to input numbers other than the ones that are being asked about in the programming problem. For instance, what happens if we try to run this program on the input 4? Well, we notice that 4 is divisible by 2, so we can multiply 4 by 3/2, and that gives us 6. 6 is divisible by 2, so we can multiply 6 by 3/2 to get 9, and then 9 isn't divisible by 2 or 5. So now we stop, and we output 9, right? So if you input 4 into this program here, it outputs 9. Finally, let's take a look at what happens if we input 20 into this program. Well, 20 is divisible by 2, so we can multiply by 3/2 to get 30. 30 is divisible by 2, so we can multiply by 3/2 to get 45. 45, we can't multiply 45 by 3/2. 45 is not divisible by 2. So again, remember that we go through the fractions one by one and see what we can multiply by. And now we can multiply by 7/5. 63, we can't multiply by either of these, so we're done. If you input 20, this program here outputs 63. This is one of the things that I really like about FRACTRAN, which is that sometimes the order of, I guess, lines, sort of, in your code don't actually matter. You could just as easily write a program 7/5, 3/2. You could switch the order of the fractions, and the program would work exactly the same. The path is slightly different to get from 20 to 63, but if you input 20 into the switched program, you do still wind up getting 63 as an output. So sometimes, but not always, the order of the fractions doesn't matter. However, sometimes the order of fractions does matter. Let's try doing the naive thing to solve this problem here. We want to turn 2 into 5, then we need the fraction 5/2. We want to turn 3 into 7, we need the fraction 7/3. We want to turn 6 into 11, we need the fraction 11/6. Now let's try this on various inputs. If we input a 2, it gets multiplied by the first fraction in the list that we can multiply by, and that's 5/2. To get 5, 5 can't be multiplied by any of these fractions, so we're done. If we input a 3, the 3 gets multiplied, well, it doesn't get multiplied by 5/2, it gets multiplied by 7/3, the first fraction in the list that we can multiply by, to get 7. And then 7 can't be multiplied by any of these, so 3 does in fact give us an output of 7. But what about 6? 6, we can actually multiply 6 by any of these fractions and get a whole number. And so the way that programs in FRACTRAN work is that you multiply the number by the first fraction in the list that you can multiply by. So in this case, we multiply 6 by, we had hoped we would multiply it by 11/6, but we're not doing that. We're multiplying it by 5/2 to get 15. Now 15, we can actually multiply 15 by, well, we can't multiply it by 5 halves, but we can multiply it by 7/3 to get 35. And now 35 we can't multiply by any of these fractions, so we're done. So we had hoped that our 6 was going to get multiplied by this fraction here, but actually it got multiplied by these two fractions here and gave us an output of 35. A key thing to note about FRACTRAN programs is that if one of the denominators is divisible by an earlier denominator, that fraction is always going to activate instead of the fraction that we want to activate. Any number that can be multiplied by 11/6 in order to get a whole number can also be multiplied by 5 halves to get a whole number, because any number that's divisible by 6 is also divisible by 2. All we need to do to fix this is to move this 11/6 to the front, and that will give us our actual answer. Now when we try inputting 6 into our program, it actually can be multiplied by 11/6 to give us 11, and then once we have an 11, 11 can't be multiplied by any of these fractions, and so we're done. We output the 11. And if we input a 2 or a 3, it's not going to, we can't multiply it by 11/6, and so the 2 is going to catch on the 5 halves, and the 3 is going to catch on the 7/3, just as we would like them to. Program problem 3 is to write a program that takes in inputs of the form 2 to the n and outputs numbers of the form 3 to the n. So 2 to the 1 should turn into 3 to the 1, 2 to the 2 should turn into 3 to the 2, 2 to the 100 should turn into 3 to the 100. Now, in a normal programming language, we would need to use logarithms to work out what n was, and then raise 3 to the power of n. But FRACTRAN isn't a normal programming language, not in the slightest. Another oddity about FRACTRAN is that we get loops for free, whether we want them or not. It turns out that the solution to this programming problem is the program 3 halves, the same as the solution to problem 0. In particular, if we input 2 to the 0th as a 1, we can't multiply it by 3 halves, so we output a 1, 3 to the 0, so that's perfectly fine. If we input a 2, as we've seen, we output a 3. If we input 4, as we've seen before, we output a 9. If we input an 8, we output a 27. So this program seems to work, but it's going to be easier to prove that it works by looking at our numbers in terms of their prime factorizations. Let's say we input 2 to the 4th, that is 16. Multiplying that by 3 halves is going to get rid of one of the 2's and add a 3. So 24. It's clear that we can multiply this by 3 halves because there's a factor of 2 in there, and when we multiply it by 3 halves, we'll lose a 2 and gain a 3. When we multiply this by 3 halves, again we can because there's a 2 there, we lose a 2 and gain a 3. And then finally, we lose the last 2, gain the last 3, and we get 3 to the 4th. And 3 to the 4th doesn't have any factors of 2, so we can't multiply it by 3 halves, so we're done. So we've turned 2 to the 4th to 3 to the 4th. So now it should be clear what's happening. We're taking the exponents of 2 in the prime factorization and moving them one by one into the exponents of 3 until we're done, and we've moved all of these 4 units over from the 2 exponent to the 3 exponent. And this is really the essence of programming in FRACTRAN. First of all, we get a free loop. We keep applying this fraction 3 halves until we can't apply it anymore. And a lot of times what you're going to want to do with a FRACTRAN program is slowly move exponents from one location to another, and maybe back or move it. We'll see various things that we can do with these exponents, but mostly it's moving exponents from one location to another one by one. Level number 4 is just a combination of level number 1 and level number 3. where we have two bases in our exponent that we're trying to move. But again, the solution is fairly simple. The fraction 3/2 keeps getting applied and will move an exponent in the 2's place into the 3's place, and the fraction 7/5 will keep getting applied to numbers divisible by 5, and will move the exponent from the 5's to the 7's. And of course, these two won't interact. Numbers with factors of 2 or 3, or maybe a combination of both, what shows up when we run one of these through, will never have a 5 in it, so we don't have to worry about this fraction interfering with this process. And numbers that show up here are going to have factors of 5 and 7, so they're never going to have 2's, so they won't be influenced by the 3/2 in the process of moving the 5's to the 7's. So the previous programming puzzles are really just to get you started with FRACTRAN and to start thinking about things in terms of their prime factorizations. When we look at a number in terms of its prime factorization, right, it's going to be 2 to some natural number, 3 to some natural number, 5 to some natural number, and so on and so forth. We're going to get some finite list of natural numbers. And so it really helps when we're trying to do programs that actually do useful things to think about the current number in the system and the numbers that show up in the fractions in terms of their prime factorizations, in terms of the way that they operate not on the individual number, but on the corresponding list of numbers, the list of exponents that we get out of the prime factorizations. So for instance, we can interpret this program here as removing factors of 3, or we can think about this program here as taking a vector of the form nm and deleting this second piece of information, zeroing it out. This is a very useful task in programming and one that we really take for granted. In fact, this vector perspective introduces us to a new programming language called VECTRAN. A program in VECTRAN is a list of vectors of integers. We input a vector into the program, all of whose entries are non-negative. At each stage of execution of our program, we add to our vector the first vector on the list that will keep it a vector of non-negative integers. If there's no such vector on the list, then we output our current vector. Programs in VECTRAN are really just programs in FRACTRAN and vice versa when we take our numbers and take their prime factorizations and then just look at the vector of exponents. Keep in mind that prime factorization works perfectly well for rational numbers, provided that you're okay with the exponents of the primes being negative, which is exactly what we have here. Our fractions correspond to vectors that have integer exponents, that is, exponents that could be negative. So let's think about what's happening here. We want to add a vector to nm that will get rid of this m. And again, because we're programming in FRACTRAN where loops are free and we want to move or get rid of exponents one by one, the sensible way to do this is with the vector 0, minus 1. If we take a vector of two non-negative numbers and continue adding 0, -1 to that vector until we can't anymore without making one of those numbers negative, that's going to take this m and gradually, one by one, decrease it until it's equal to 0. We can translate this back into FRACTRAN by taking these numbers as the powers of respective primes. So 2 to the 0, 3 to the -1st, 5 to, if there was another number, 7 to that, 11 to that, and so on and so forth. So in this case, it's 2 to the 0th times 3 to the -1st, or 1/3. So our program in FRACTRAN should be 1/3. And we can check, sure enough, if we repeatedly multiply by 1/3 until we can't anymore, to numbers of the form 2 to the n, 3 to the m, we wind up getting numbers of the form 2 to the n. It gets rid, step by step, of all of the 3's that show up in the prime factorization. Let's take a look at a level that we've already done from the perspective of these prime factorization exponent vectors. Here there are 4 primes in play, so we want to be thinking about these numbers as vectors of 4 numbers. So here we want to turn 2 to the n, which is just going to be 2 to the n times 3 to the 0 times 5 to the 0 times 7 to the 0. We want to turn vectors of this form into vectors of the form 2 to the 0, 3 to the n, 5 to the 0, 7 to the 0. So essentially what we're doing in programming problem 4 is moving data from the 2's register to the 3's register. I like to call these registers and number them by the prime that they correspond to. So this is the 2's register, the 3's register, the 5's register, and the 7's register. And similarly, we want to move data from the 5's register to the 7's register. 2 to the 0, 3 to the 0, 5 to the n, 7 to the 0 becomes 2 to the 0, 3 to the 0, 5 to the 0, 7 to the n. We're moving data from the 5's register into the 7's register. Now if we translate our solution, 3 halves, if we prime factor 3 halves, that's going to be 3 to the first and a 2 to the minus first. So because 3 halves is 2 to the negative first, 3 to the first, the vector that it corresponds to is negative 1, 1, 0, 0. What this vector does in our program is it checks, first of all, can we even subtract 1, move 1 counter out of the 2's register, and then move it into the 3's register. Decrement the 2's register, increment the 3's register, if we can. If we can't, this vector doesn't apply. Similarly, 7/5, that's equal to 5 to the minus first, 7 to the first, so it corresponds to 0, 0, negative 1, 1. And that vector tells us if we can decrement the 5's register and increment the 7's register. Applying these two repeatedly will take counters one by one from the 2's register to the 3's register and from the 5's register to the 7's register. Another thing that we take for granted but is absolutely essential in almost any programming language is the ability to duplicate data. A program that takes numbers of the form 2 to the n and turns them into numbers of the form 3 to the n, 5 to the n is essentially taking vectors of the form n0, 0 to vectors of the form 0, n, n. We're taking data from the 2's register, removing it from the 2's register, but duplicating it into both the 3's register and the 5's register. A straightforward way of solving this problem is to realize that 3 to the n, 5 to the n is actually equal to 3 times 5 to the n, or 15 to the n. So really this is the same as our problems for turning 2 to the n into 3 to the n, or 5 to the n into 7 to the n, except now we have a 15. But it's no different. The program that does this is just 15 halves. Every time we see a 2, we'll turn it into a 15, and that'll slowly, one by one, turn the 2 to the n into a 15 to the n. If we want to look at this program from the perspective of VECTRAN, well, if we prime factor this, we'll get a 3 to the first and a 5 to the first from the numerator, and a 2 to the minus first from the denominator. In other words, our program is negative 1, 1, 1. This program here, if it can, removes a counter from the 2's register and adds a counter to the 3's register and the 5's register. And so you can follow it when you run the program as it turns powers of 2 into powers of 3 and powers of 5 simultaneously. At some point, we're going to want to do some basic arithmetic tasks, like adding two numbers together. We can't hope for a program that takes in numbers n and m and outputs the number n plus m for two reasons. First of all, we don't have programs that take in more than one number, And second of all, this can introduce arbitrary prime factors. The only prime factors that a FRACTRAN program can introduce are those that appear in the prime factorizations of the numerators of our fractions. So we can't hope for straightforward addition of the inputs, but that really isn't how FRACTRAN works. Remember, it's best to think of things in terms of vectors. This program here takes in the input nm0 and outputs 0, 0, n plus m. It takes the contents of two registers, clears those registers, and adds the contents together and puts that in the 5s register. Yet again, I find it helpful to think about the contents of these registers as like a pile of counters. And our goal in this case is to take all of the counters out of the 2 pile and the 3 pile and move them into the 5 pile. And it just so happens that the number of counters we want in the 5 pile happens to be the sum of the number of counters in the 2 and 3 piles. We should think about these tasks as being separate. We want to move counters from the 2's pile to the 5's pile, and we also want to move counters from the 3's pile to the 5's pile. This will take counters from the 2's pile to the 5's pile, and this will take counters from the 3's pile to the 5's pile, and they correspond to the fractions 5 halves, 2 to the negative first, 5 to the first, and 5 thirds. 3 to the negative first, 5 to the first. So these will be the fractions in our program, and it doesn't matter what order we have them in. And here you can see this in action on various inputs. Another way to see this is to try our program specification where m equals 0. We then notice that this program has to take numbers of the form 2 to the n to 5 to the n. And so that suggests maybe we should try having 5 halves as one of the fractions in our program. When we check to see how the 5 halves by itself behaves on these inputs here, that suggests that a fraction of 5 thirds will take us the rest of the way. So this is how we interpret and perform the basic task of addition, but notice this winds up clearing the input registers, and sometimes you don't want that. The problem is, if we somehow figured out a way to move data from the 5's place back to the 2's and 3's place, so that we had, n, m, n plus m, our program would want to take the data in the 2's place and the 3's place and multiply it by 5 halves and 5 thirds, and that would, get rid of the data here and put data that we didn't want in the 5's place. We're going to have to be extra tricky in order to come up with a version of addition that doesn't clear the input registers. An important thing to note is that there isn't a conservation of counters. In our addition case, there was a conservation of counters. All of the counters in the 2's place and the 3's place could be thought of as moving into the 5's place, but that doesn't necessarily have to be the case. We could take the number of counters in the 2's register and double them into the 3's register, essentially turning vectors of the form n0 into 0 to n. And this is another level that's really straightforward if you remember your exponent rules. 3 to the 2n is the same as 9, that is 3 squared, to the n. And so just like before, turning 2 to the n into 5 to the n, or 7 to the n, or 15 to the n, or 9 to the n, it's all the same. We can do this with the fraction 9 halves. This corresponds to the vector -1, 2, that every time it takes a counter out of the 2's register, it puts 2 counters into the 3's register. This next level is a little bit of a cheat. It shouldn't matter how you get your program to do a particular task, just as long as it does that task. But in this case, I think it's educationally useful to try to figure out how to get a program to turn 2 to the n to 3 to the 2n that doesn't involve any 9's. Our previous solution, because it involved 3 to the power of 2 in it, had 9s in it, had factors of 9. So let's think back. What solutions to previous levels could we apply in this case? Well, we had a previous level where we were doubling the total number of counters, the sum of the exponents. And that was the level that took 2 to the n to 3 to the n, 5 to the n. So maybe that's a good start. If we can take 2 to the n to 3 to the n, 5 to the n, and then turn that 5 to the n into more 3 to the n's, maybe that will work. And it turns out that it does. In order to turn 2 to the n into 3 to the n, 5 to the n, we had 15 halves, no 9s there. And then in order to turn 3 to the n, 5 to the n into 3 to the 2n, we're trying to move counters from the 5's register to the 3's register. And to do that, we just have 3/5. In some sense, what we're doing is we're conjuring up a new register. We have an infinite number of data registers that we can store information in, one for every prime number. Our initial program involved numbers in the 2's register and the 3's register, but by having the 5's register as an intermediate register, we were able to accomplish this programming task. This is very similar to creating a new intermediate variable in a standard programming language, and has lots of really important practical uses that we'll see in future problems. Another important arithmetic operation is subtraction. In this case, let's make things easy. Let's assume that the number in the 2's register is strictly less than the number in the 3's register. And our goal is to get rid of the content of the 2's register and the same number of counters from the 3's register. So if you think about that, how can we do that? Well, we pick out counters from the 2's register and the 3's register simultaneously until the 2's register is empty. In terms of vectors, we're trying to turn nm into 0 m minus n, and the way to do that is to repeatedly remove one counter from both registers. This corresponds to the fraction, well, it corresponds to 2 to the negative first times 3 to the negative first, which is just 1/6. Of course, what do we do if the number in the 2's register is larger than the number in the 3's register? As we've seen, a very useful strategy is to try running previous programs on new inputs. So what happens if we take a number of the form 2 to the n, 3 to the m, where n is larger than m, and run that through the program 1/6? Well, what that's going to do is it's going to pull counters out of the 2's register and out of the 3's register, but this time the 3's register is going to empty first, and we'll be left with 2 to the n minus m. And if they're equal, we wind up getting 1, right? Both piles drain simultaneously. So we can put an equal to sign on either of these. Well, this number here is exactly the number we want here in the output. It's just in the wrong register. In this case, it's in the 3's register. In this case, it's in the 2's register. In either case, we should move it into the 5's register, and that will be our desired output. So after we do 1/6 until we can't, we'll want to, in order to move from the 3's register to the 5's register, multiply by 5/3. In order to move from the 2's register to the 5's register, we multiply by 5/2. And so this program here, as we can see on various sample inputs, winds up computing this correctly. It's worth noting that we really only have two ways of decrementing a register. One is uncontrolled decrementing that register, as we saw in our deleting example, where we just take out counters until we can't anymore. In these past two examples, we've seen controlled decreasing of a register, where we're using one register in order to control how much we're decreasing another register. We don't necessarily have to stop when that register is empty. We can also stop when the other register is empty. But unfortunately, this process will empty out one of the two registers. FRACTRAN turns out to be very well suited for doing modular arithmetic on exponents. Because again, if we think about each of these registers as piles of counters, we can take away as many counters at a time as we want repeatedly until we can't anymore. Here I'd like to take out 2 counters at a time from the 2's register until I can't anymore. And that just corresponds to 2 to the negative 2, or the fraction 1/4. After taking a number of the form 2 to the k and multiplying by 1/4 until we can't anymore, we'll either have 2 to the 1st if k was odd, or we'll have 2 to the 0th if k was even. Which is almost what we want, except we want it to be the case that we output 3 if k is odd instead of 2. And so we actually need another fraction to turn that last 2 into a 3. This fraction here won't affect any of the other 2's because they'll catch on the 1/4 beforehand. It'll only catch on that very last 2. It's worth noting that if we tried to modify the specification of the program, we're going to run into a little bit of trouble, right? Suppose we wanted to output a 5 if k is even. Well, there's a problem. Once we reach 1, hopefully there aren't any fractions in our list that we can multiply by. If there was, then there would be a fraction in the list with denominator 1. And we can always multiply by a fraction with denominator 1. So at no point would this program halt. The program would run forever because at the very least it can multiply by that fraction with denominator 1. And I guess there is a place for programs that keep running forever if you interpret some of their intermediate values as kind of being outputs. And in fact, Conway does this to create a program that just constantly spits out prime numbers. An important aspect of programming that we haven't talked about yet is conditionals. We would like to, for instance, take the value in the 2's register and conditional based on whether there's an 11 or a 17, either add 1 to that value in that register or subtract 1 from the value in that register. In some sense, we're using the values in the 11's and the 17's register as a Boolean, a 0 or a 1. And this is a very important part of working in FRACTRAN. In the previous levels, we've really only considered exponents as being natural numbers. But to think of them as Booleans, restricting them to be either 0 or 1, making sure that they stay within 0 or 1, winds up being incredibly useful. It gives us a new data type to work with. And in fact, I'd like to go one step further in terms of how we're thinking about how these registers are being used. When programming in FRACTRAN, it's useful to have a series of registers whose values are always going to be 0 or 1. For instance, I like to designate the primes in the teens as control variables, and I'm going to want the values in these registers to all be Booleans, but I'm also going to want only one of those Booleans to be true at any one time. And we can interpret the question of which of the Booleans is true as a representation of state data. For instance, here I will say that the program is in state 11 because the 11 register is the one that has the 1 in it, 1 representing true. And here, for values like this, I'll say that the program is in the 17 state because the 17 register is the one that has the 1 in it, and all of the other control primes have an exponent of 0. Having some sort of state variable is essential to all sorts of different types of programming. It's the thing that makes finite state automata work at all. If you're working with Turing machines have, in addition to their tape, a state from a finite collection of possible states to indicate what sorts of tasks they're working on. And if you want to think about a more traditional program, you can think about the state as kind of what line of the program are we at in terms of execution? There's only finitely many lines of the program, and following along as we go through line by line and maybe jumping from one line to another as we have loops or possibly gotos, that information tells us a lot about what we're currently doing within the program. So we can interpret what this problem is telling us as saying, if we're in state 11, add 1 to the 2's register, and if we're in state 17, subtract 1 from the 2's register. Of course, this thinking isn't really helpful in terms of actually figuring out the program that does this. The program that does this, it should, well, if there is a factor of 11 present, and we can detect that by putting an 11 in the denominator, then we should multiply by 2. And so we can put a 2 in the numerator in order to accomplish that. And this will also get rid of the 11, which is a thing that we want to do here. In order to detect the presence of a 17, well, we need to have a 17 in the denominator, and that will also get rid of the 17. And then we want to divide by 2, so we'll put a 2 in the denominator as well. There's nothing in the numerator, so we'll put a 1 there. And this is our program. You're welcome to turn this 17 times 2 into a 34, but that just obfuscates the code. I don't recommend doing this. The FRACTRAN interpreter that I've built is perfectly fine handling products. But of course, this doesn't really capture the idea of a state. The idea of a state is that if we're in some state and then we do something, we should then be in a state. This is really capturing the notion of some sort of Boolean control. What we'd really like to do is say, if you're in state 11, start moving, and if we're going to be turning 2 to the n into 3 to the n, the process for doing that is always to multiply by 3/2, to move counters from the 2's register to the 3's register one by one. And in order to have that happen, we need to be able to say, if you were in state 11, continue to stay in state 11, all the way through all of the steps, every step of moving the counters from the 2's to the 3's register, and ending in state 11. To somehow keep that 11 present, to distinguish it from this situation where if we see a 17 instead, we'd like to keep that 17 around, and that 17, if we're in state 17, tells us stay in state 17 but move the counters from the 2's register to instead the 5's register. So we need to somehow do this. And the naive thing to do, well, we want to turn 2 to the n times 11 into 3 to the n times 11. So first of all, we need to detect if there's an 11 there, right, to distinguish it from this case. So we'll put an 11 in the denominator. And we also want to remove a counter from the 2's place. So we'll put a 2 here to do that, and we want to add a counter to the 3's place. And this is all well and good. This will accomplish our task, except it gets rid of the 11. We're dividing out by that 11. We'd like to put it back. Again, the naive way of doing this is to just put it back in the numerator. But there's a problem. This fraction cancels. If we just had the fraction 33 over 22, 3 times 11 over 2 times 11, in our program, it would also act on the case where there's a 17 present and not an 11 present, and we don't want that. So how can we avoid this situation? So here's the trick, and I figured out this trick by reading Conway's paper on FRACTRAN, which is instead of going from state 11 to state 11, let's have an intermediate state. Let's say instead that we want to go from state 11 to state 13. Now, this isn't quite going to accomplish our task because then we're going to be in state 13 and we're not really sure what to do if we're in state 13 yet, right? This isn't going to create a loop in and of itself. But what we can then do is move from state 13 back to state 11 without changing anything else. And this will actually accomplish our goal. Let's say that we started off in 2 to the 4th times 11. Then we would multiply by this first fraction here. There's both a factor of 2 and a factor of 11 present, So we'll get rid of one of the 2's, we'll get rid of the 11, and we'll add a 3 and a 13. Now with this number here, of course this number isn't divisible by 2 times 11. It has a 2, but it doesn't have an 11, so it's not going to be divisible by 22. But it is going to be divisible by 13. It has a 13 in there, so it will catch on this fraction here, 11/13. And that will just turn the 13 into an 11. And so this will carry out one step of the process, moving the counters from the 2's register to the 3's register. If we continue doing this, it will work all the way down to 3 to the 4th times 11, and then notice that because there's no 2, we can't apply this fraction here. And so it isn't going to catch on either of these fractions. We're just going to stop at 3 to the 4th times 11, which is the thing that we wanted. So having these 2 fractions here allows us to carry out the task of moving data from the 2's register to the 3's register, provided that we're in state 11. And then analogously, 5 times 19 over 2 times 17 and 17/19 will carry out this task here, detecting whether or not there's a 17 present, and if there is a 17 present and a 2 present, then we're going to start moving those 2's into the 5's place. And keep carrying out that task, switching back and forth between state 17 and state 19 until we've moved all of the 2's into the 5's place, and then we'll stop at 5 to the n times 17 as desired. Usually when I'm programming in FRACTRAN, I like to label out what each fraction should do, and then use that to figure out what the fractions are. For this program here, we would like a fraction that says that if we're in state 11, multiply by 3/2, and we'd really like to stay in state 11, but again, we can't do that because then we get that canceling that we saw before. So instead, we will go to state 13. And when we're in state 13, we don't want to do anything. We just want to go back to state 11. And the same thing with states 17 and 19. We can then turn these into fractions. This fraction here should get rid of an 11 to get out of state 11, and add a 13 to get into state 13. And it should also multiply by 3/2. This fraction here, in order to get out of state 13 and into state 11, we need to multiply by 11/13. This fraction here, in order to get out of state 17 and into state 19, is going to need a 19/17. And we also need to multiply by 5/2 out front. Turn it into a single fraction. And then, of course, if we're in state 19, get rid of the 19, replace it with a 17. That'll be 17/19. And having like a list in order of if we're in this state, do this task, go to this state, is really useful. And if we're careful about the order that we put these instructions in, that will tell us what the correct order to put our fractions in is. In this case, it doesn't really matter what order the fractions are in. Figuring that out on your own is quite a tricky puzzle to solve. I had to look at Conway's paper on FRACTRAN in order to figure this out. But I've added in kind of a hint level as level 15 if you want kind of an intermediate step in terms of figuring out level 14. This is a basic program where we're executing a single task, in this case either adding or subtracting 1 from the 2's register, and then switching states. If we're in state 11, we'd like to go to state 13, and if we're in state 17, we'd like to go to state 19. And there's no loops here. We're not interested in doing some operation over and over again. There's nothing to do if we're in state 13 and nothing to do if we're in state 19, except return. This fraction here, we're trying to turn an 11 into a 13, so that's going to look like 13/11s, and we also need to multiply by 2, so there's going to be a 2 in the numerator there. For this fraction, we're going to turn a 17 into a 19, so 19/17. And we also want to multiply by 1/2, so we're going to put a 2 into the denominator. And so these are our two fractions. This is our program. 2 times 13 over 11 and 19 over 2 times 17. Having control primes gives us the ability to do things that we couldn't do before. Remember that we couldn't write a program to turn 2 to the n into 5 if n was even, and 3 if n was odd. And specifically, the only reason why we couldn't write a program to do this is because if n is equal to 0, this is 1. We would like to turn 1 into 5. And of course, in order to turn 1 into anything else, we need to have a fraction in our program that has a denominator of 1. But if we have a fraction in our program with denominator 1, then our program is never going to be able to halt. So it's impossible to write a program to do this task. However, if you make an exception and say, if n is equal to 0, we want it to output 1 instead. Don't do anything to that 1 because we can't do anything to that 1. Then you can write a program to do this, and I challenge you to do so. Having these control primes present allows us to avoid the situation. Even if n is equal to 0, the input here is going to be 11, and so we don't have to worry about accidentally running into 1. This is very convenient because we want to have control primes anyway to keep track of what kind of line of our program we are currently at. And the solution to this level is very similar to the solution to level 12. We want to get rid of counters in the 2 register in pairs. So we'll start by multiplying by 1/4 until we can't anymore. And what that will do is that we'll take this number here and reduce this power of 2 until we can't multiply by 1/4 anymore, leaving us either with 2 times 11 or just 11, depending on, we'll get 2 times 11 if n was odd and just 11 if n was even. And so now we want to turn 2 times 11 into 3 and 11 into 5, and we can do that. We need to be a little bit careful about the order of these fractions. Note that 11 divides into 2 times 11, so we need to have the 2 times 11 come first, because otherwise, if we're at 22 and this 5/11 was first, this would catch on this fraction here. And so we'd multiply this by 5/11, and we don't want to do that. We want to turn this into a 3. We want to turn this into a 5. A naive way of implementing a FRACTRAN interpreter is to, whenever we encounter a fraction of the form p over q, determine whether or not the current number is divisible by q, and if so, divide it by q and then multiply by p. And this works perfectly well, assuming that p over q is in fully reduced form. However, this sort of perspective leaves us wanting to have fractions in our program that aren't fully reduced, and have those fractions still act the same way. Check to see if the number is divisible by q, and if so, divide by q and multiply by p. For instance, we saw a desire to have a fraction in our program that checks to see whether the current number is divisible by 22, and if so, to divide out 22 and multiply by 33. To have a fraction that requires an 11 to be present in order to activate, right? This is different from the simplified version of this fraction, 3/2. 3/2 activates on any number that's divisible by 2. But what if we wanted a fraction that only activated when the number was divisible by 2 and 11? But again, we wanted our fraction to not actually get rid of that 11. Having an 11 in the denominator is going to get rid of an 11. And so we want to put it back. And so we want to put an 11 in the numerator. This is a very reasonable thing to do in programming in FRACTRAN. But of course, you can't do this. You can't have a fraction that behaves this way as part of a FRACTRAN program. all fractions in a FRACTRAN program will behave like their fully canceled forms. The way that we write the fraction doesn't matter, it's just the value of the fraction that matters. But it's really tempting, we would like to augment FRACTRAN to some sort of FRACTRAN++ that adds the ability to write in fractions that aren't fully reduced and treat them the way that you would want them to. We would like it to be the case that our FRACTRAN allows us to write things like this, and it will behave the way that we want. It will multiply by 3/2, but only if there's an 11 present, and it won't get rid of that 11. But of course, one of the things that you have to worry about when you augment a programming language is, have we changed its expressive power? The goal of this video and the goal of the interactive was to demonstrate to you that FRACTRAN, not FRACTRAN++, was Turing complete. So if I show you instead that FRACTRAN++ is Turing complete, well, that doesn't really tell you anything about FRACTRAN until I show you that any FRACTRAN++ program can be turned into a FRACTRAN program. And it can. All I need to do is show you that anytime we have one of these uncancelled fractions that we'd like to behave in an uncancelled way, we can somehow replace it. We can somehow modify our whole program, replacing this fraction and maybe adding a few more fractions to make everything work out, in order to make it an original FRACTRAN program that behaves the way that our FRACTRAN++ program behaves. And I've done this. I've created a mode that I call no cancel mode that allows you to write your programs in FRACTRAN++, where this is perfectly meaningful and behaves the way that you would want it to, and then it compiles the code into original FRACTRAN. But in order to unlock this, you need to demonstrate that you can do this sort of transformation on your own. The goal of this transformer is not to figure out this step for you, but rather to save yourself from having to do something that you've demonstrated that you know how to do. And in order to demonstrate that you know how to do this, this level, 17, requires you to write a program that behaves like the fraction 55,000 over 22,000, a fraction that's very much not fully simplified. So how can we do this? Well, I've sort of lied to you a little bit. We have to, in order to actually have a fraction like this, in order to actually compile this out, we need to have a prime that we're assuming that we're not using. But that's perfectly okay. The programs that we write in FRACTRAN assume that the input is in some very limited form, and we only introduce finitely many primes through the numerators of the fractions in our program. So let's assume that we're trying to write a program, and that program, the prime 13, doesn't show up at all. And we would like to simulate having this fraction as part of our program. Then what we'll do instead is replace this fraction here in our program with 13 22,000ths. This fraction sort of works like this. It certainly activates in the same situations, except instead of putting back 55,000, it puts back a 13. And so what we want to do then is, at the very beginning of the program, put in a fraction that has a 13 in the denominator and 55,000 in the numerator. And we don't have to worry about inserting this new fraction at the beginning of the program, changing the behavior of the program, because we assumed that the prime 13 never actually showed up in the operation of the program. Never shows up in the input and never shows up, it's never introduced by any of the fractions. So what this means is that in pretty much all situations, this fraction here at the very beginning will just get completely ignored because the number isn't divisible by 13. But when we do catch on this fraction and introduce a 13, at the very next step, we'll catch on this fraction because there's a 13 present, because we made there be a 13 present. And that's exactly what we wanted to do. We want this 13 to turn into a 55,000 right away before the program has the opportunity to do anything else to our number. So now that we've demonstrated in this level that FRACTRAN++ is essentially equivalent to original FRACTRAN, my FRACTRAN interpreter will now offer the option of writing programs in no cancel mode. And this is extremely useful because it automatically deals with the real reason why we want no cancel mode is so that we can deal with situations where we're in a particular state, right? The control prime is a particular value, and we want to do something, and we want to stay in that particular state. And again, you can code your way around this, but it's really convenient to not have to. And so for the rest of the levels, I'll be showing you the solution in FRACTRAN++, where I'm allowed to do something like this, allowed to go from state 11 to state 11 without having to introduce a brand new state and then go back to state 11. Let's take a look at something that we really couldn't do before, and that is take a piece of data and duplicate it, but leave it in place. Right? There's a strong reason to believe that we can't write a program that takes in inputs of the form 2 to the n and turns them into inputs of the form 2 to the n, 3 to the n, because whatever our program does when it sees a 2 to the n, it's going to want to do to this proposed output. It's going to want to continue operating on this value here as if it were a 2 to the n, because it sees a 2 to the n. And everything works out in terms of factors, so we can kind of ignore this 3 to the n present. But having control primes allows us to avoid that situation. Our program is going to do one thing when it sees 2 to the n times 11. When there's an 11 present, it knows to do one thing to 2 to the n's, and when there's a 17 present, it knows to do something else to 2 to the n's. So it's not going to try to do whatever it did to the original input to the output. Now, in order to make this happen, we're going to want to do this as a two-step process. We're first going to want to turn 2 to the n into 3 to the n, 5 to the n, and then turn the 5 to the n's back into 2 to the n's. And of course, there'll be control primes present to keep track of which phase of this process we're at. So let's write out what we want this program to look like. So we have 4 different commands that we'd like our program to do. First of all, if we're in state 11 and there are any 2's present, right, there's some non-zero value in the 2's register, we'd like to move one counter into the 3's and 5's register and out of the 2's register. This is kind of the duplication that we've done previously. And we'd like to stay in state 11. Of course, we can't really do that. We have to create state 13 and then go to state 13 and then go back to state 11. But with this no cancel present, we don't have to worry about coding that for ourselves. The compiler will take care of that. So this operation here turns into the fraction. Well, it detects if there's an 11 present, and it detects whether there's a 2 present, and if so, it multiplies by 15 halves, and doesn't get rid of that 11, so we have to put the 11 back. So this is the fraction that does this, and again, we have to compile this out. This is in FRACTRAN++. On the other hand, if there aren't any 2's present, so we're going to want this fraction to be after this fraction. If this fraction didn't catch, but there's an 11, it's because there aren't any 2's. So if we're in state 11 and there aren't any 2's present, well then we're done with this process of moving all of our values out of the 2's register and into the 3's and 5's register. And so we'll want to go to state 17 in order to initiate the second stage. And that's simply the fraction 17/11. If there is an 11 present, that is, we're in state 11, get rid of that 11 and put a 17 in there. And again, we don't have to worry about this fraction activating if there are 2's present, because this fraction will activate first instead. Next, if we're in state 17 and there are any 5's present, multiply by 2/5 and stay in state 17. Continue looping in state 17. And again, technically we should create a state 19 and then go back to state 17, but we don't have to worry about that. The compiler will handle that for us. So if there's a 17 present and there are 5's present, multiply by 2/5 and then put the 17 back. And then finally, if we're in state 17 and there isn't any 5s present, then we're done. And of course, in order to have this, we simply have to not have a fraction present to handle this particular case. So our program is just these 3 fractions, and again, that's going to compile this. This is a program in FRACTRAN++. It's going to compile into the FRACTRAN program that looks like this, and it's going to behave like this on the test inputs. At this point, we have a proper programming language here. We can use these control primes in order to indicate separate lines of code or different tasks that we're working on and kind of jump between tasks depending on what needs to get done. So how can we do a task like multiplication? So here I have kind of a first guess at what our program could be. The idea here is that we want to take the value in the 2's register. Notice that in the input, the 5's register starts off empty. It starts off with a 0 in it. And what we want to do is we want to take the value in the 2's register and add it to the value in the 5's register. And then we want to subtract 1 from the value in the 3's register, and then do that again. So we'll keep taking the value in the 2's register and adding it to the value of the 5's register, and keep subtracting 1 from the value in the 3's register over and over again until the value of the 3's register is 0, until there are no more 3's left. And so this might look something like this. In state 11, right, we start off in state 11, we want to move all of the 2's to 5's. And this is a process, we'll do this step by step. So we need to repeat, right? We need to go back to state 11 until we've moved all of the 2's. If there are no more 2's left, then we want to jump to state 17. In state 17, we want to subtract 1 from the 3's place, and then jump back to state 11. And if we're completely out of 3's, if we can't subtract 1 from the 3's place, then we want to jump to state 13, and in state 13 there's no instructions, so we halt. The problem is this program doesn't quite work because in state 11 we're moving all of the 2's into the 5's place, and so there's nothing left in the 2's place once we're done with that. And so, we go to state 17, we subtract 1 from the 3's, we go back to the state 11, and there's nothing in the 2's register to move into the 5's place. We need to somehow restore the original value in the 2's register before we do this process again. But luckily we can fix that. We've seen before how we can take the value in a particular register and copy it. And a big part of programming in FRACTRAN is taking the value in a register and duplicating it so that we have the value stored in a safe place, so that when we modify the original register, because operations within FRACTRAN require modifying the values in registers in order to get any sense of what value is in there, and then restoring that value because we have a saved copy of it. So what we'll want to do is we'll want to take the value in the 2's register and store it in, let's say, the 7's register so that we can bring it back when we need it. So one possible solution, and there are many, looks something like this. If we're in the 11 state, that is, there's a 11 control prime present, we first want to move all of the 2's to 7's. Now, it doesn't actually matter when we do this copying, right? At this stage, we could move the 2's into 7's and 5's, or we could move the 2's into 7's and then later on move the 7's back to the 2's and then also add that value to the 5's at the same time. It doesn't matter when we do this duplication process, but we need to do it at some point. So we're going to move the value from the 2's register to the 7's register, and this is going to require repeatedly multiplying by 7/2. That is to say that if the 2's register is non-empty, if we can, multiply by 7/2 and then repeatedly do this, continue being in state 11. Then if we're in state 11 and there are no more 2's left, we want to subtract 1 from the value in the 3's register and go to 17. So of course, how do we subtract 1 from the 3's register? we want to multiply by 1/3. And if we can't do that, if we're in state 11 and the 2's are empty and the 3's are also empty, so we can't do either of these two things, then we're done. We want to go to state 13. 13 is going to require a little bit of cleanup, but we're pretty much done at this point. So what this is going to look like in terms of fractions, this first one is going to look like, well, if we're in state 11, we want to multiply by 7/2, and we want to put that 11 back. So it's going to look like this fraction, and again, this is in FRACTRAN++. We're going to compile it into ordinary FRACTRAN. This second operation, well, if there aren't any 2's left, we can't multiply by this fraction, and so we want to switch states from state 11 to state 17. And then we want to multiply by 1/3. I guess we don't need that 1 there. So this next step is going to look like this fraction. Next, if we can't multiply by either of these fractions, because there isn't a 2 and there isn't a 3, but there is an 11, there's no more 3's, we want to go to state 13, so that requires multiplying by 13/11. Next, if we're in state 17, we want to move the value from the 7's register to the 2's register and the 5's register. The way to do that is to incrementally multiply by 10/7. And of course, we can only do that if the 7's are non-empty. So we're in state 17, we're going into state 17, and we want to multiply by 10/7. Next, if we're in state 17, but we can't multiply by this fraction here because there are no more 7's, we want to go back to state 11, so we get rid of the 17. We put the 11 back. If we're in state 13, it's because we were in state 11, we were doing this thing, and we ran out of 3's. We had added all of the copies of n into the 5's register that we wanted to, and the 3's register is empty, so we're done. We have our product. The thing is, if you run the program like this, you wind up getting these results that there's still stuff left in the 7's register. One of the things that's useful if you're trying to program advanced programs in FRACTRAN is to run the program, and then maybe it requires a little bit of cleanup in order to do what you want. In this case, we see that the program operates correctly, but there are a bunch of 7's that we don't want. And so all we need to do is, when we're done, clean up those 7's. So if we're in state 13 and there's any 7's left, we want to multiply by 1/7 and stay in state 13. This is going to look like 1 times 13 over 7 times 13. Really, we don't need these 13's here because the only way to be in state 13 is to not be in state 11 or state 17. That is, you've passed by all of these fractions already. But it's kind of nice to have this here anyway, just to indicate we really only want this fraction to activate if there's a 13 present. And this will clear out the 7's register, and once there are no more 7's, there isn't going to be a fraction to multiply by, and so that indicates that we should halt. So this is our program, and it does in fact multiply. This level's quite tricky and probably takes some guessing and checking, trial and error, in order to get the order of things right. The first time I tried to write a program to do this, I accidentally got like 5 to the n times m minus 1, which you can clean up at the end, but that's a little bit inelegant. So of course, if we have the ability to multiply values, we can use this as part of larger programs. In order to, for instance, if we want to square a number, well, all we need to do is duplicate it, set everything up so we can use our multiplication program, and then use it. So one way to do this is to start off with, well, we have our number in the form 2 to the n times 19, and we'd like to turn that into something that we can input into our multiplication function. So 2 to the n times 3 to the n times 11, right? We want the control prime to be the appropriate thing for the input to our multiplication function. So our multiplication program will take this and output 5 to the n squared times 13, as desired. But it's a little bit inefficient to do things this way. We've seen that the program to duplicate data in place is a little bit complicated. It's a two-step process in and of itself. And actually, it would be easier to instead duplicate the data not in place. We could instead take our original 2 to the n times 19 and duplicate that data not in place, turn it into 3 to the n, and I guess move that data into the 23s register as well. We're kind of running out of registers, right? We want to, later on, we want to use our multiplication function, so we shouldn't use any registers that we use in our multiplication function in this part, just to make sure that there's no interference between these two parts of the program. And then we'll have a slightly modified version of our multiplication function that, instead of multiplying the contents of the 2s and 3s register, multiplies the contents of the 3s and 23s registers and puts them in the 5s register. This modified multiplication function is super easy. We just take all instances of 2 as a factor in our original multiplication program and replace them by 23s. So that's how we do this step. What about this step, duplicating the data from the 2s register into the 3s and 23s register? Well, that's just if we're in state 19 and there are 2s present, then we want to multiply by 3 times 23 2s, and then stay in 19, and then no 2s present. Then we want to go to 11. So this first step is going to look something like 3 times 23 times 19 over 2 times 19. And then this step here, if we can't multiply by this fraction because there are no 2s, but we're still in state 19, we just want to go into state 11, which will activate our multiplication program. So we have these two fractions followed by a modified version of our multiplication program, replacing 2s by 23s. The solution looks like this, and here's what happens when we run it. If we're going to have a practical programming language, we need to have various data types to store different sorts of data. By default in FRACTRAN, we're storing natural numbers within a finite number of registers, right? We can check how many different primes our program is using just by prime factoring the fractions of our program. And we have one register that stores a natural number for each one of those. And we've seen how by carefully ensuring that a particular register only contains a 0 or a 1, we can store booleans, and we can use that to, for instance, store state data. But what if we wanted to store some more complicated data? Remember that the goal for this video and the goal for the interactive is to eventually show that FRACTRAN is Turing complete. So we want to be able to build a Turing machine in FRACTRAN. Well, what do we need to build a Turing machine? We need the ability to talk about the tape of the Turing machine. And the tape is an array of characters, and the characters come from some finite collection of symbols. And it turns out there's a very natural way of storing these sorts of arrays that makes basic operations on the arrays correspond to basic arithmetical operations. And that is, we want to store our array of data as the decimal digits of the exponent of a particular number. If we're careful, we can use digits 0 through 9, but it's actually easier to just ignore that and use the digits 1 through 9, so we don't have to deal with leading zeros. And the idea is simple. We will use these exponents as stacks, where the top of the stack is the 1s digit. Suppose that we're storing the array 2, 3, 4, 1 within the 2s register. And suppose that we wanted to pop one of the digits off the stack, in particular the one on the top of the stack. What we can do is we can divide this number by 10. That's going to give us 234, remainder 1. And so this is going to be the new value that we want to put on the stack. This is the stack with the top element removed. And then this is the element that we removed from the stack. And then if we want to put data back on the stack, all we need to do is multiply by 10. So if this is the current value of the stack, and then let's say we wanted to push a 5 onto the stack, well, we'd take this number, we'd multiply it by 10, and then we'd add 5, and that would give us the stack with now a 5 on top of the stack. Now, of course, this only works if you want the values on your stack to be digits from 1 to 9, or using a coding argument, you can represent, 9 other things that could be on the stack. Of course, if you wanted more things on the stack, you'd have to use a different base. The mathematics is the same, but of course, reading the very convenient thing about working in base 10 is that reading the contents of the stack is trivial. And it turns out we won't need more than 9 characters. We won't need nearly that many in terms of implementing the example Turing machine in the last level. So how can we do this? It turns out we don't actually need control primes. It turns out that we want to turn 10 counters at a time in the 2's register into single counters in the 5's register. And then when we can't do that anymore, the remainder will just be left in the 2's counter. Admittedly, we kind of want the remainder to be in a separate register and the quotient to be in the 2's register, because that kind of agrees with our intuition about popping a piece of data off. And the quotient gives us our stack with the popped element removed. So this is our new stack, right? And we can think of, having the stack that we're dealing with being in the 2's register, but mathematically it's going to be easier to implement it this way, and then in practice we're going to have to do some switching data around in order to get the data where we want it to be. But again, super straightforward. We're just trying to turn 10 counters at a time from the 2's register into single counters in the 5's register. And that just looks like 5 over 2 to the 10. If we apply this fraction repeatedly to a number of this form, we're going to wind up getting 2 to the r, 5 to the q times 11, and we just need to turn that 11 into a 13, so we'll throw in a fraction of 13/11 as well, and this is our program. It's a really simple program, but it's carrying out a really important task, popping data off of a stack. Dividing by 10 is super easy, but dividing by an arbitrary number is a bit trickier. This level here, we're doing arbitrary division. Technically, this isn't necessary for building our Turing machines. And in fact, once you've proved that you can build a Turing machine, then it's obvious that you can build a machine that performs this particular calculation. I guess you kind of have to take the input data and put it on the Turing machine, and then run the Turing machine, and then interpret the output of the Turing machine. But those steps will be fairly straightforward. So technically this level is unnecessary, but it's a good exercise in programming in FRACTRAN. The first thing that we're going to want to do is we're going to want to pull one copy of n out of the exponent of 2. And in order to do that, we need to subtract, we need to remove counters from both the 2's register and the 3's register. And then when the 3's register is empty, we'll have removed n counters from the 2's register. And of course, we want to keep the value from the 3's register. This is an important value, and we can't just get rid of it. So we'll put it in the 7's register for safekeeping, and we can bring it back later at a different stage of execution. So this is a repeated process, and what it winds up translating into is multiplying by 7 over 2 times 3. This gets rid of one counter from the 2's place, one counter from the 3's place, and puts one counter in the 7's place. So once we've applied this fraction until we can't, we'll have subtracted n counters from the 3's place, and then we'll have subtracted n counters from the 2's place, and then we'll have added n counters into the 7's place. Again, for safekeeping this value here. Although not quite. It could be the case that we actually run out, so we could run out of 3's first, in which case we could have subtracted an n from the 2's, and then we'll want to, continue our process of subtracting out copies of n from the 2's. But it could be the case that we're actually done. This is 2 to some small remainder that's smaller than n, and so when we try to subtract out n counters from the 2's and 3's, because there are fewer counters in the 2's register, we actually run out on the 2's register first. So that's one possibility. If we run out on the 2's register first, right, we can't multiply by this because there are no 2's. So we're going to want to switch into 17, which is going to be our cleanup state, before we switch into 13 when we're finally done, we're finally ready to present our output. But I want to be careful. I need to specify if there are no 2's, but there are 3's left, then we're done. Then we should do cleanup. If we run out of these at the same time, then we still need to, nowhere along the lines did we increment the 5's register. We need to increment the 5's register. We need to do that as kind of a separate step. If we can't multiply by 7 over 2 times 3 because there are no 3's, then we've finished subtracting one copy of n from both the 2's register and the 3's register, and so we want to increment the 5's register to indicate that we've done that, and then we need to restore the value of n to the 3's register. It's currently in the 7's register where we put it for safekeeping. We need to put it back in the 3's register. And we'll go to state 19 where we'll do that restoration from the 7's register to the 3's register. So let's do that. Let's specify how we're going to restore the data from the 7's register to the 3's register when we're in state 19. So this is very straightforward. We just need to repeatedly multiply by 3/7 until we can't anymore. We'll stay in state 19. We'll kind of loop in state 19 until we've done that. And then finally, when there are no 7's, we'll go back to state 11 because n has been restored to state 3. So we're back to where we started, except 5 now contains an incremented quotient value, and the 2's register has been decremented by n. So this repeated process of going back and forth between state 11, where we're subtracting n from the 2's and 3's register and putting it in the 7's register, and then once we've finished that, because the 3's register is empty, we go to state 19 to restore the value of the 3's register, and we keep doing that in a loop until we've subtracted out all of the n's from the power of 2. We'll have incremented the 5's register once for every time we've done that, so Q is going to be stored in the 5's register, and R is going to be stored in the 2's register, and we just need to clean things up. So what happens if the value in the 2's register is small? Well, again, we're going to be taking away values one by one from both the 2's register and the 3's register until one of them is empty, right? That's what happens here. And we're going to run out when the 2's register is empty. So at this stage here, the 2's register is empty. We have to somehow restore this remainder value back to the 2's register. And the question is, where is that remainder value? Well, it turns out that remainder value is actually in the 7's register, because each time we subtracted 1 from the 2's and 3's register, we added that value to the 7's register. And so we've done that once for every counter in the 2's register. So we need to take the value from the 7's register and move it to the 2's register. When we do this operation, there's also going to be some leftover values in the 3's register. Remember, we're emptying the 2's and 3's register at the same time. When the 2's register is empty, there's probably still going to be some stuff in the 3's register. Maybe not. If they both empty at the same time, then there's nothing in the 3's register. But generally speaking, there's still going to be values left in the 3's register, and we don't want that in our output. So we want to clear the 3's register. So in addition to multiplying by 2/7 as many times as we can to get the data out of the 7s register and into the 2s register, we also want to multiply by 1/3 as many times as we can just to clear the 3s register. And then finally, if we can't do either of these, if the 7s register has already been emptied and the 3s register has already been emptied, then we switch to state 13, which is going to be our halt state. And of course, we just implement the halt state by not having a fraction associated to it. So let's translate these into fractions, right? To go from state 11 to state 11 and multiply by 7/6. Again, in FRACTRAN++, that's 7 times 11 over 2 times 3 times 11. To go from state 11 to state 17, we need 17/11ths. And it's actually important to detect whether or not there are 3s here. So I'm going to want to add in a 3 to this denominator here. We don't care about the value in the 3s register. We're going to be getting rid of it anyway. So it's perfectly fine to get rid of one of those and not have to restore it. This just detects, makes sure that the 3s register is not empty. If there are no 3s, we need to add 1 to the 5s register by multiplying by 5, and then switch to state 19. So we're going from 11 to 19, and we're trying to multiply by 5s. So that's going to be 5 times 19 over 11. To go from state 19 to 19 and multiply by 3/7, that's going to be 19/19 and 3/7. And then to go from state 19 to state 11, we need 11/19. To go from state 17 to state 17 and multiply by 2/7, we're going to want 17/17. And again, we multiply by 2/7. And then we also want 1/3 times 17/17 to get rid of all of those copies of 1/3. And then finally, to switch from state 17 to 13, if neither of these fractions activate, we want to next have the fraction 13/17, and we don't want any fractions with denominators 13, so our program just stops running once we're in state 13. So this is our program for division here. Of course, we have to compile it from FRACTRAN++ to ordinary FRACTRAN, but that's perfectly fine. We're used to doing that by now. And you could use this as kind of a subroutine in more advanced programs like, for instance, detecting prime numbers. So you could imagine a situation where we have in one of our registers a stack consisting just of 1s and 2s, and we want to interpret this as a sequence of instructions. Right, starting with the top of the stack and then working our way down, because that's the easy way to work through this number. We want to apply these operations to something. You could imagine maybe these are like different sorts of instructions, and we're actually doing some proper coding here. But I think a really simple example is to view each of these as kind of a permutation on the primes 23, 29, and 31. So at any time we're going to be, I don't want to use the word state because we already have state variables here. The 11 is our state variable, but this is kind of our like secondary state. So this variable here is going to take care of the state of our program, like what line of code our program is on. And that program is going to be simulating what's called a finite state automaton. And this is just a machine where we are in one of these 3 states in this case. And the idea is that we're going to read these characters one by one, and they're going to change which of these automaton states we're in. When we read a 1, if we're in state 23, if there's a 23 present, we're going to go to state 29. If we're in state 29, we're going to go to state 23. And if we're in state 31, we're going to stay in state 31. On the other hand, if we read a 2, we're going to apply this function here. If we're in state 23, we wind up in state 31. If we're in state 29, we wind up in state 23. If we're in state 31, we wind up in state 29. If you're curious about finite state automata, I have an entire video series about them and their relationship to model theory, and I'll link that down below. But for now, all we want to do is read out the contents of the 3's register, interpret that as a list of instructions, as a stack containing 1s and 2s, and interpreting these as instructions describing how we should switch which prime is active, whether it's 23, 29, or 31. This program here, we only want to apply the operation once. In the next level, we'll do the more advanced thing of applying each character one by one. And so in the 3's place, we're going to have either a 1 or a 2. So this is either going to be 3 to the first or 3 to the second. And we just want to apply the appropriate transformation to which prime is active. And then we'll do that repeatedly in order to kind of read off an entire stack of instructions in the next level. Now, this program is actually really straightforward. You just have to interpret what's going on, right? We want it to be the case that if we have a 3 to the first times 11 times 23, that becomes 11 times f sub 1 of 23, which is 29. If we have 3 to the 1 and we read a 29, we want to go to 11 times 23, right? F sub 1 of 29 is 23, and F sub 1 of 31 is 31. And then we want F sub 2 is going to turn 23 into 31. And so how do we write a program that maps these 6 concrete values to these 6 concrete values? Well, we just need one fraction for each mapping that has to happen. In order to get this to happen, we need the fraction 11 times 29 over 3 times 11 times 23, and so on and so forth. There's only one slight catch. If you try to run this program, it's not going to work. And the reason why it's not going to work is because if we input this number here to this list of fractions in this order here, it's going to catch on this fraction here, right? 9 times 11 times 31 is divisible by 3 times 11 times 31. Right? It's just this is this times 3. But we don't want it to catch on this fraction here. We want it to catch on this fraction here. And so what we need to do is we need to take these fractions and move them to the front of our program so that they catch first. And of course, we don't have to worry about 3 to the first times 11 times 31 catching on 9 times 11 times 31 because we don't have divisibility there. So our program ultimately looks like this. So now let's have a level that carries out a list of instructions. This time we're going to store our stack of instructions, either 1s or 2s, in the 2's register. And we're going to apply them. It's not really going to matter what prime we start with, but let's just say that we're only going to apply them to 23s. And then our goal is to turn that 23 into the appropriate one of 23, 29, or 31, depending on the instructions in the stack in the 2's register when we started. So for example, if we start off with 2 to the 122 times 11 times 23, we're going to want to first get rid of this 2 and then apply f of 2 to this 23. So f sub 2 of 23 is 31. Then we're going to want to pop another 2 off of this stack, and we're going to want to apply f of 2 again. So apply f sub 2 of 31. So that's going to take us to 29. And then we read a 1 on the stack, so we pop that off, and we're left with 2 to the 0th. And we need to apply f sub 1 to 29, which is going to take us to 23. And then, of course, we need to turn these 11s into 13s at some point to indicate that we're done. So how are we going to write a program to carry this out? In our starting state, in state 11, we're going to want to move the tens digit and higher from the twos register and store that somewhere safe. Right, this is just a division by 10. And the value that's left over in the twos place is just going to be the ones digit, and that's going to give us the instruction that we want. So once we've done that, once we've finished this process here, we want to copy the remaining value, the ones digit from the twos register, into the threes register, right? To kind of set it up to use our previous program, which had the value either 1 or 2, which function we wanted to apply in the threes register. So we want to copy this value to the threes register. Then we're all set up to use the previous program. Right, we start off this block in 3 to the I, where I is 1 or 2, depending on the value that we want to implement. 5 to the Q, where Q is kind of the remaining digits in the tens digit and higher from the twos place originally, the rest of the stack that we needed to save. The 11 to indicate that we're in state 11, and then the P to indicate the state of our finite state automaton. And then we'll use our previous program. Our previous program doesn't care about fives, they'll just kind of pass through, and that will take us to 5 to the Q times 11 times f sub I of P. It will get rid of the value in the threes place, and then change the prime based on which function we needed to change the prime by. So then our next step is to get the value back from the fives register into the twos register. Remember, this is our stack. Once we've removed the instruction that we want to apply, we've applied the instruction. We need to get this stack back into the twos place so we can recurse, so we can do this over again. If there are any twos left that we still need to keep executing, so we need to swap back to state 11, go back to the beginning of this, where we can apply the next instruction. And if not, then we're done, and our program, so for some reason this level, I require you to get rid of the 13 in the end, so let's get rid of the 13. And then since we won't be in any state, we won't have any control primes active, the program will just halt, because all of these will require some control prime to be present. So how do we translate this? Well, again, moving the tens digit and higher from twos to fives, that's very straightforward. That's just going to be 5 over 2 to the 10. And again, we have to repeatedly apply this process, and that's going to require multiplying by 11 over 11 to stay in state 11 and keep applying this process until we can't anymore, because there aren't 10 twos. It's worth noting that if the power of 2 is large enough, it's going to take forever to get rid of that exponent, just taking away 10 counters at a time. So for instance, you could speed up the process with something like 5 to the 10 over 2 to the 100th times 11 over 11, and just have that fraction operating in parallel. If we can take away 100 counters at a time from the twos register, do so, add 10 counters to the fives register, and if not, then take 10 counters away from the twos register and add 1 counter to the fives register, and that'll speed up the program fairly significantly. But we don't need it. It doesn't affect the mathematics of things. Then we need to copy the remaining twos. Note that the twos register might not be empty. We just know that it has fewer than 10 counters in it. And we need to copy the remaining twos into the threes place. So that's going to look like this. Then we have our previous program, making sure that everything has an 11 over 11 in it, in case you didn't have 11 over 11 in each of your fractions for the previous program. And then finally, to go to 13, that's just 13/11. That'll take us to state 13 if none of these fractions apply, because we're done with everything. In state 13, we need to move all the 5s back to 2s. That's very straightforward. We're just going to, in a loop, multiply by 2/5. If there are any 2s left, we need to swap to state 11. That's going to require not only checking to see if we're in state 13, but also checking to see if there are any 2s left. But of course, this denominator here is going to get rid of a 2, so we need to put that 2 back, and again require our FRACTRAN++ compiler, the no cancel operation, to kind of handle this for us. And then finally, if neither of these fractions are applicable, there's no 2s left, there's no 5s that we have to move, then we need to get rid of the 13, and that's just going to be 1/13, and that's our program. So our program looks like this, and we need to insert our previous program from the previous level, so all in all it's going to look like this. So far we've just been reading from our stacks of digits, but we can also write to our stacks of digits just as easily. If we have a stack of digits, we can add a new digit onto the top of the stack, that is the 1's place, by multiplying by 10 to shift everything over, and then adding the digit that we would like to add onto the stack. We can perform a very interesting operation just by popping values off of one stack and then pushing them onto another stack, and that is to reverse the contents of the stack. Reverse the digits of our number. Suppose that we started off with 1,234 in the 2's register, so this is a stack representing the sequence 1, 2, 3, 4, and an empty 3's register. Let's see what happens as we pop values off of this stack and push them onto this stack. So first we pop the 4, remember that the 1's digit is the top of the stack. We pop the 4 off and we push it onto the 3's. And again, in order to push onto a stack, we multiply by 10, that does nothing here, and then we add the value that we want to push onto the stack. The next value that we pop off this stack is 3, and we'll push that onto this stack here. Again, we multiply by 10 and add the value that we want to push onto the stack, and so now we have 2 values on our stack, 4 and 3. And after we've popped all of the values off of the 2's register stack and pushed them onto the 3's register stack, we have the reverse of the original stack. So we have an operation that can reverse the digits of a number, and that's exactly what we're trying to do here for this problem. So let's actually build a mechanism to do that. And it's just going to require a component to pop digits off of the 2's register stack and then push them onto the 3's register stack. Notice that we start off in state 11. So what are we going to want to do in state 11? We're going to start off, and this process is going to be a big loop. So we want to start off with 2 to the 10 times a, so this is going to be everything else that's on the stack, plus n, and this is the value that we'd like to pop off the stack in this particular iteration of the loop. And then 3 is going to have a value on its stack that's multiplied by 10. Right now it doesn't have, at the very start, it doesn't have anything on the 3 stack, but it'll turn out that this is what we want to be on the 3's stack at this stage of the iteration of the program. We want to do some stuff, and this is going to take us into the next state, maybe not 13, 13 is our end state, so 17. And what we want to do in this step is we want to pull this 2 apart. We want to extract the value of a, and we want to extract the value of n. Now, if you were making this program up for yourself from scratch, you'd probably want to have a separate step where you extracted these two values, a and n, into two separate registers. So, you know, like 5 to the a, 7 to the n, something like that. But it turns out that we'll want to take this value of n and add it on to the value of the 3's register. So we don't actually need to take n and move it to another register and then move it back to the 3's register. We'll just move it onto the 3's register. And then the value of a, we're going to want to move into, let's say, the 5's register. So that's going to be our first step, which is popping a value off of this stack, pushing it onto this stack. In order to remove a value from this stack, we're going to need to take a, we're going to need to move it into a separate register, and then move it back into the 2's register. And so that's what this process is. We've done kind of half of that process. We can't do that process all in one step, because then we'd have values coming back to the 2's register that would then get sent back to the 5's register or whatever, and would form an infinite loop. But we can do half of that process in this step here. And then the next step, we'll take this value of a and we'll push it back to the 2's place. So in state 17, we're going to do some modifications to this, and ultimately we'll wind up in, when we're done, we'll wind up in state 19, which is going to finish that process of moving a to the 5's register and then back to the 2's register. Now the next thing that I want to do is I want to take the value in the 3's register. This is the correct value, and so we'll have a branch here at some point that will say, oh, okay, if we're done with this process, finish and enter the return state 13, and of course we won't have anything to do if the control prime is a 13, and so the program will halt. But in order to get there, this value here in the 3's register had to be 10 times b. What we're actually seeing is this is actually part of a process that's kind of already started from the previous loop of multiplying the value on the stack by 10 and then adding the value that we want to push onto the stack. So we need to do that multiplication by 10, specifically to this value here, which is currently on the stack. And again, the way to do that is a two-step process. We're first going to take this value and we're going to send it off to another register, and then when we send it back, we'll multiply it by 10. In state 19, we're going to do some stuff and then enter state 11 afterwards to kind of finish the loop. So what do we need to do in order to finish the loop? Well, we need to send this value in the 7's register. The 2's register is what we want it to be. The 7's register, we need to move back to the 3's register, and we need to multiply by 10 in order to kind of set up this process here. So this here is going to be, we popped the value of n off of this stack here, and so we're just left with what was in the 10's place and higher in the 2's register. And then for this value b, there's a 0 at the end, but we've taken this n and we've kind of popped it into the 10's place. And of course, maybe your program looks a little bit different. There are other ways of optimizing this program. There are certainly more straightforward ways of translating the given task into a program. That's perfectly fine. And so at this point, we're going to want to branch off. If we have the value that we want in the 3's register and there's nothing left from this stack here, so there's nothing in the 5's register, then we're going to want to go into state 13. Okay, so this is the structure of our program. Now let's work out what that's going to look like in terms of the code. In state 11, we're first going to want to move values in the 10's place and higher from the 2's register into the 5's register. So this fraction will do that. This fraction here will move the remaining values in the 2's register into the 3's register. Remember that the 1's digit in the 3's register, starting off the loop, was 0, and so it's just going to take the value from the 2's register and replace the 0 by that. If neither of these apply, if we've totally emptied out the 2's register, then we're mostly done with step 11. We need to decide, though, where we go on the branch. Do we go to state 13? Are we done? Or are we not done? Do we go to state 17 and continue the cycle? Remember that the thing that we wanted to check was whether or not there was a 5. If there are 5s, then we want to continue the cycle. We want to go to state 17. And we can do that check with a fraction like this. This fraction will only activate if we're in state 11 and there's a 5 present, but it won't get rid of that 5 because there's also a 5 in the numerator to put that 5 back. And again, this is improper, but we can compile it out. On the other hand, if there are no 5s left, then we're done with our loop, and so we want to go into state 13. And this fraction will only activate if the 5s aren't present. Now, in state 17, we had 2 goals. We wanted to move everything from the 3's register into the 7's register so that we could move it back and multiply by 10 when we did that. And we also wanted to restore the value from the 5's register back to the 2's register. So this fraction here will move all the values from the 3's register into the 7's register. Again, we're looping, and so we keep applying this fraction until we can't anymore, and that's going to take all the values from the 3's register and move them to the 7's register. And then we just want to move everything from the 5's register into the 2's register. And once we've finished those processes, there aren't going to be any 3's or 5's left. And so what fraction do we want to apply? Well, we want to switch into state 19, so we'll get rid of the 17 and we'll add a 19 in order to do that. And again, this fraction will only activate once these 2 fractions have done their thing. In state 19, we wanted to move the values out of the 7's register back to the 3's register, but multiplying by 10 when we did so. So this fraction here will do that. It takes 1 7 out of the 7's register, and it adds 10 counters into the 3's register. And of course, keeps us in state 19. And when we've finished with that, we want to go back to state 11 to complete the loop. So this is our program here. Let's take a look at it in action. Let's say that we start off with a 1, 2, 3 in the 2's register, and let's watch that get reversed. Well, the first thing we can do is we can apply this fraction here, and we can apply it repeatedly until we've gotten rid of everything but the 1's digit from the 2's register. I'm going to get rid of the 1 and the 2, and those are going to move into the 5's register. So by repeatedly applying this fraction 12 times, we're going to wind up in 2 to the 3rd times 5 to the 12 times 11. Now, we can't apply this fraction anymore, so let's try this fraction. Well, we can apply this fraction 3 times to move this 3 from the 2's register into the 3's register. Now, we can't apply either of these fractions because there isn't a 2 left, so can we apply this fraction? Well, there's a 5 present. This is divisible by 5 times 11, so we can apply this fraction. I'm going to replace the 5 times 11 by 5 times 17. So now we can't apply any of these fractions because there's no 17, so we start off here. We can apply this fraction here 3 times in order to move this 3 into the 7's register. We can apply this fraction here 12 times in order to move this 12 back into the 2's register. And then we can't apply any of these fractions, so we apply this fraction here, and we go from state 17 to state 19. We can't apply any of these fractions. We can apply this fraction here 3 times to move this 3 from the 7's place into the 3's place, but it's going to multiply by 10 when we do so. And then we can't apply any of these fractions up until this one, so we switch from state 19 to state 11. So as you can see, what we've done in this cycle here is we've taken this 3 and we've pushed it onto the 3's register, and then we've made sure that there's always going to be a 0 at the end when we get back to this stage of the loop. So this process is going to continue. We're going to move the 2 into this register here, so that's going to be 2 to the first times 3 to the 320th times 11 after we loop around again. Now let's follow what happens next after this stage here. We can't apply this fraction because there aren't at least 10 counters in the 2's register. We can apply this fraction here that's going to move that last counter from the 2's register into the 3's register. Now, for this one, we can't apply either of these fractions. We can't apply this fraction because there aren't any 5's, and that's the key thing, right? If there were more than 10 counters in the 2's register, there would be 5's, and then we'd continue the loop until there weren't. But now we've hit the stage where there are no 5's, and so this fraction doesn't apply, and so this fraction does apply. And that's going to cause us to go into state 13. And again, by convention, there's nothing to do in state 13, so we halt. So we've taken this input and we've reversed it. And now comes the disappointing part of this video. I had hoped to come up with a solution to level 25 that created first a Turing machine to determine whether or not a particular number was a palindrome, and then convert that Turing machine into a corresponding FRACTRAN program. But that's incredibly tedious. It's far more tedious than I had originally anticipated when I made that level, and due to time crunch at the end of the Summer of Math exposition, I wasn't able to fully test out this level to find out that it was incredibly tedious to do this. But that really isn't the goal of the last level of the FRACTRAN interactive. The goal of the last level is for you to convince yourself that FRACTRAN is Turing complete. And there's a wide variety of ways of doing that besides just implementing a Turing machine. First of all, I hope it's been clear by the way that I present these things that if you wrote out a program in a very simple assembly language, you could very easily convert it into a FRACTRAN programming language. And there's a wide variety of very simple theoretical assembly languages. Of course, all real assembly languages aren't Turing complete because they're run on actual computers, which only have a limited amount of memory. Everything is a finite state automaton. But there are some theoretical assembly languages that have very few instructions that we could compile to FRACTRAN. Because hopefully it's clear that we have the ability to jump between quote-unquote lines of our code, which are really these control primes, these states that our programs are in. We have the ability to conditionally jump. It's going to be a little bit tricky to conditionally jump, for instance, with like an inequality, checking to see if the value in one register is larger than the value in another register. We would have to like copy the values from both of those registers into registers that aren't currently being used, and then dump them both simultaneously and see which one was left, which one emptied out before the other one. But you could do that. It would require splitting a single instruction up into several different instructions. One to copy all of the values, one to make sure that the values were being restored, and another one to make sure all the values were being properly dumped. But at the core of FRACTRAN is the ability to conditionally jump based on whether the value in a particular register is equal to 0 or not. And some of these Turing complete assembly languages only have that version of conditional jump. So that's perfectly fine as well. We've seen how we can access arbitrary memory with arbitrarily large stacks. So we have that. That's really the essential piece of what it means to be Turing complete, is the ability to access arbitrary amounts of memory. If you don't have that, then you're a finite state automaton. And we've seen how to do basic arithmetic operations, although again, that requires us to take a single instruction and break it up into a bunch of smaller instructions that get executed in loops. But that's perfectly fine, and in fact, a lot of these Turing complete basic assembly languages only have like add one or subtract one operations from each of the registers. So again, if you're familiar with these particular types of theoretical assembly languages, or Minsky machines, or counter machines, it should be clear that FRACTRAN is Turing complete. But if you're not, then you really do want to see me implement a Turing machine, so let me show you roughly how to do that. Let's say that we wanted to represent a Turing machine whose tape at a particular time looked something like this. Now, normally you'd probably want to put like zeros and ones on your tape, but I want to avoid zeros because I'm going to be storing the value on this tape as the digits of the exponent in various registers. And so to avoid any issues about leading zeros, I'm just going to put 2s and 3s on the tape instead of 0s and 1s, but this doesn't affect what we can compute with this particular machine. So let's say that these are the current values on the tape, and the read-write head is at this particular position. How can we represent this particular setup in FRACTRAN? Well, I'm going to want to represent it where we actually split the values for those on the left-hand side of the read-write head, the value at the read-write head, and the values to the right of the read-write head. We're going to take these values here, and we're going to store them on a stack in the 2's register. And we're going to make sure that the 1's digit is the one that's closest to the read-write head. So these are going to be copied in order. Then we're going to store in the 3's register the value currently at the read-write head. And then we're going to store in the 5's register the stack of values to the right of the read-write head. But we want the top of the stack to be closest to the read-write head. So we're actually going to flip the order of these numbers here. We want the 1's digit to be closest because that's the value that we're going to have to access. If we wanted to move this read-write head 1 unit to the right, we would need to take this value here, and we would need to, first of all, if we move this 1 to the right, we're going to push this 2 onto this stack here. And so we want it to wind up in the 1's place here, so we have 2, 3, 2, 2 on this stack here. And then we want to take the 1's digit off of the 5's register. We want to pop this value off the stack and then push it onto the 3's register. So that's the new value in the 3's register, because we want to move the read-write head over here so that this 3 is now in the 3's register. So that's why we want to store this 3 in the top of the stack in the 5's register, because that's the next thing that we want to access. On the other hand, if we want to take this read-write head and move it 1 unit to the left, well, we're going to have to take this 2 and pop it off of this stack and put it onto the 3's stack. But I guess first we're going to have to take this 2 and pop it onto the 5's register stack so that we have 2, 2, 2, 3, 2 on the 5's register stack. So by storing our registers in this fashion, it's really straightforward to move the read-write head back and forth. It's also really straightforward to change the value at the read-write head. That's just changing the value in the 3's register. We can just put an appropriate fraction, the appropriate power of 3, in the numerator and the denominator. We're then going to want to store, obviously, this whole system is going to require a lot of control, right? Each movement of the head, each step of the Turing machine is going to require carrying out a lot of different instructions. It's going to require taking the value from the 3's register and pushing it onto the appropriate stack, and then popping a value off of the other stack and moving it into the 3's register, and we're going to want that to be a separate step, and so we're going to need a separate control prime to correspond to those separate steps. We're going to need a bunch of states, a bunch of different control primes to keep track of where we are in the process of executing our code. But we're also going to want to, because we're implementing a Turing machine is more than just a tape and a read-write head. It also has an internal state to it. There's a finite number of internal states that the register can have, in its execution. And we're going to want another set of primes. So we're going to have our control primes, but just like in the case of implementing a finite state automaton, we're also going to want to have a separate set of primes to keep track of what state our Turing machine is in. And so this is going to be how we're going to represent a particular configuration of our Turing machine as a number, and that should hopefully inspire you as to how to implement this thing in FRACTRAN if you want. But again, this is incredibly tedious. I think you should consider yourself to have won the FRACTRAN game if you've convinced yourself that FRACTRAN is Turing complete. Now, I very deliberately made the choice of having the last level be something like recognize palindromes because I wanted it to be possible for you to solve this level without building a Turing machine. The intention was that you would first convince yourself that FRACTRAN is Turing complete, realize that it would be incredibly tedious to actually implement a Turing machine in FRACTRAN, and then cheat by taking the input, reversing it using our reversal program from the previous step, and then checking to see if the two were equal to each other by just draining both registers at once. And so hopefully if you did complete this level, you completed it that way. Although if you didn't, if you actually built a Turing machine, let me know. Paste your code down in the comments below. I'd be really curious to see this. But I do hope that the tedium of trying to build a Turing machine in FRACTRAN hasn't dissuaded you from the ability to actually do practical programming tasks in FRACTRAN. A lot of programming tasks that we can break down into various loops and then ifs and then whiles and things like that, and basic arithmetic pieces can very easily be implemented in FRACTRAN just by writing out what we'd like the program to do in various states and then translating those into proper fractions. And then, of course, compiling from FRACTRAN++ into ordinary FRACTRAN. So it really is a practical programming language. And in fact, John Conway and various collaborators have actually created really interesting programs in FRACTRAN. For instance, a program that prints out all of the primes. So this program here, you'll notice that it has a 1 in the denominator, which I said that you really shouldn't have because that forces your program into an infinite loop. Well, it turns out this program, you want an infinite loop. This program is going to, you just start it off with the input 2, and then you'll run the program, and every so often the number that we're at is going to wind up being a power of 2. And if you look at those powers of 2, it's just going to be primes. Similarly, there's also a program that runs infinitely that prints out the digits of pi. So I hope this video was able to convince you that FRACTRAN is at least somewhat practical to program in, and is also a Turing complete programming language. In another video, I'll talk about the philosophical consequences of the fact that FRACTRAN is Turing complete and what that means for the Collatz conjecture. In the meantime, if you have any questions or comments or have worked out any interesting programs in FRACTRAN, feel free to leave them down below in the comments, and I hope to see you in a future video.